All right, here we go with the second lesson of this statistics unit. One variable data and probability we get to eventually. I don't know if I mentioned that yesterday or not. We're going to look at data distributions, so the types of patterns in data that are really common. And we're going to look at one of the ways, we'll look at creating one of the types of graphs we looked at yesterday. So our first one that we're making ourselves. Before we get to that, let's just review over the types of data. So they could be numerical or, right? So the discrete and the continuous are numerical, or numbers. And so discrete is the ones where you're just counting numbers, number of chairs in a room, number of floors in a building, whatever, stuff like that. I think that's actually one of the ones here. So this is just counting numbers. 1, 2, 3, and so on. Continuous comes from measurements. Okay, so you're going to have decimals. You're going to have an estimated number, really, right, in any measurement. And then categorical, it's kind of weird how you describe it, but basically it's just a word. It's an answer to a question, right? So when we're looking at these things, we're going to label everything as either discrete, continuous CON, or categorical CAT. So the height of a building, you're welcome to press pause as we go through this. I'm going to be taking it up as we go, of course. But the height of a building is something you're measuring, right? So if you're measuring, then that would be continuous. Number of rooms in a house is literally something you would just count. That'd be discrete. Number of floors in a building, also something you just count. So discrete. The sum of the areas, so if you're calculating all the square footage and so on, that'd be measurements, right? So that'd be continuous. Favorite TV show, that'd just be a word answer, so that, like it's whatever show you say, that'd be categorical. Grade in an English class, be 72.3% or whatever it is, so that's obviously like sort of a measurement, right? So that would be continuous. Someone's age. So I might put a star on some of these on a test and say, if you could argue one way or the other or both, even justify, right? So for this one, I think you could say, like, if it was just in years, then that would be discrete. But if it was, in months and weeks and days or whatever, months, weeks, and days. I don't know if you've had any discussions with new parents, but ask how old their child is and be like, oh, 3 months, 2 weeks, and 3 days. Be like, wow, that's really precise. That's basically like a continuous data point at that point, right? You're measuring down so much. Like, sure, you don't want to break it down to minutes. Anyways, number of cancer deaths last year, that'd be just a counting thing, so discrete. Paint color in your bedroom is just a word, right? So that would be a categorical. Volume on an iPod. This is another one where we could describe more than one, justify it in more than one way. So some numbers on the volume are just, like on my television in my living room, for example, is literally just 1, 2, 3, and so on. And if the volume is higher than 12 or 13 or 14, inevitably I end up saying, hey, turn that down to my daughters, kind of thing. That would be discrete. But some have, some seem to have like any amount. You can have any volume you want, right? It's not restricted to just 1, 2, 3, 4 or whatever. And so if it seems like it can be any volume, there's no number associated with it, then not that there's no number, but because you can certainly measure the volume in decibels or something, right? So let's say if it was the actual sound level and you're just measuring it with a device in decibels is the unit for sound, then that would be continuous. Calories in a meal, right? That would just be something you could measure, of course, right? It can be continuous because you could weigh out the number of grams of the meal and the type of food and look up how many calories per gram it is and so on. So that'd be continuous for a measurement. Okay. All right, so now we're on to the distributions of data that are really common. Okay, there's these certain shapes that always sort of come up when you take do surveys. And so this one here, to start it with, it says time of birth for all babies born in Canada in one day. There's really no reason for babies to be born earlier in the day or later in the day. It could equal chance everywhere, right? And so you get this, what's called a uniform distribution. Okay, so in this case, the data are approximately distributed evenly. There's really no higher chance of one versus the other. Okay, so if you're looking at this as just a graph picture, that bar graph is nice, but basically, it's just like you have like equal chance sort of everywhere, right? So that would be a uniform distribution if you're taking a note or something. You don't want to copy down the entire bar graph or histogram. Actually, this is right. So this is a histogram because there's no spaces. So, and what we're looking at is the types of patterns that are really common that show up when you have a bunch of data taken from some kind of survey. Okay, so the uniform distribution would just be there isn't any particular value that's more likely than another. Another really common type is a normal distribution, or a bell-shaped distribution, they call it. So if you look at this one, of course, the bell shape is pretty obvious here, right? Where you have this, like literally like a church bell kind of thing. Bells, well, like, I don't know, not that kind of thing, right? And they have like a thing that goes inside and makes the ringing sound, right? So this is a bell-shaped distribution. Cancel that. Smartboard's a little off again today. Just delete that with the keyboard here. There we go. So your bell-shaped distribution is this, right? You have this. And so the reason for that shape is you have in here most of the data clustered in the middle. In the middle, meaning that we have the tails going off sort of equally on both ends, right? It's not lopsided, it's symmetrical. And so the tails off, and I'm going to say tails off like evenly or symmetrically. Evenly or symmetrically. And so what's happening here is the most likely result is in that middle, right? So here we have the most likely result. Right? If you're getting any given answer from a survey, that'd be your best bet would be to guess that one. Of course, lots of values are possible, but that's the most likely one, right? So in this case here, it was marathon times. So like, there's a typical time that it takes people that do marathons, and some people do it faster because they're insanely in shape, and some people do it longer because they're not as in shape, or they're just doing it as a life goal bucket list kind of thing, but they're not really shooting for a certain time. They're not trying to give themselves a heart attack or anything. Okay, so that's a normal shape, and so the normal or bell distribution is that. It's really common. Skewed left. Okay, so this one, you want to think of this shape as looking like this. It's kind of like there's a bell shape or normal, but it's skewed off to the left. There's like this skew off to the left like that. So there's more data extending out to the left, but the majority of the data is kind of backwards logic and naming here. The most common result is on the right, is to the right of the distribution. It's called skewed left because the skew is the big long tail. Okay, so the tails off, skew, or the tail off is to the left. Okay, so it's like this, off to the left like that. Okay, so really we have our distribution, we have our pattern like that. Like you took a normal distribution and kind of like stretched it out to the left. That's why they call it that. Okay, so again, it kind of seems backwards, right? But most of the data is on the right. That's something weird. You have to kind of just keep that in mind. So the most likely is, of course, on the right end of the distribution. And then, of course, skewed right is pretty obvious, right? Skewed right is the opposite of that. So we'd have the graph tails off to the right. most of the data is on the low end, and but it's been distorted out along to the right. Okay. So we have vacant apartments based on rent. You know, that first one. So you can picture like the higher the rent, the less likely they are to be rented, I suppose, because people can't afford them. It's fairly easy to think of examples of why data might be like this. So, you know, if I was thinking of a sport where the averages are sort of higher than normal for heights, right? So height versus just like the frequency of players or whatever, right? But so you think of like basketball players, for example, they're really tall in general, so you're going to have a cluster up to on the higher end because there's an advantage. Then you know there some shorter NBA players that are quite effective. This might be based on points or something, right? So height versus points, and so you have some players that yeah. Oh, actually, it should have been the other way around. I was just like thinking of that. It should have been points versus height based on what I was saying. So tall players tend to get more points, but then you know, are there some players that do well even though they're not as tall in basketball? Certainly, that's possible, right? Okay, that as well as I could. Where am I at here? Getting messed up because the smart board's wonky on me today. All right, so this one is really common. Time of eruptions. Yeah, so with Old Faithful, there's like two common times, but you know, it varies a little bit. Even though it's Old Faithful, it's not always the exact time that it erupts, but there's two times during the day. So that's one example of a bimodal. Another example is in teaching. Teachers tend to be pretty familiar with the bimodal distribution because you have students on this region here that, you know, show up and try. That's pretty much the two biggest indicators of success in high school, right? Going to class and trying. And then you have this group over here that maybe isn't showing up as much and isn't trying as much. So you have these two groups. Think of it as the group that gets it and the group that doesn't. Usually it's because of those factors are the biggest indicators for sure. Correlation between attendance and trying and success is pretty big, obviously. So I'm going to put here not so much. So yeah, the histogram has like these two distinct peaks, basically like it's two normal distributions in one. Okay, let me pause the video quick here and align things for the next task. All right, here we go. So trunk circle or pie graphs. This one shows, you know, a survey of asking 24 high school students what their plans are after graduation. And so people have answered college, university, or work. And so, one sec here. So we have a bunch of answers, right? Well, it's a nice way to look at a bunch of numbers like that instead of trying to count and lose track of which ones and so on. As you go, you'd say, okay, college, we have one there, and another college, okay, there's another one, and so on, and tick, tick, tick as you go. And you do a tally chart and you cross them off as you've counted them, right? And so you end up with your 14 of those and so on, right? So you'd have 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, kind of thing as you go. And same thing for the university and work, and you end up with this big tally chart of everything you have, right? Now, what we want to do is we want to be able to make a circle graph or a pie graph. And so what we need to do is we need to calculate what percentage of the whole circle these things are. So I think I'm going to copy this to that circle page so I can do it all in one. Go here. All right. There we go. So let's go here. So the 14, right? Basically, for each one, we need to figure out the angle that corresponds. So angle that represents each number each frequency as a portion of the whole, right? So the angle that represents each frequency's portion of the whole. Something like that. And so for this one, for the 14, I would encourage you to think of it as like it's 14 out of, I'll communicate a lot of things here, but so it's 14 out of 24, right? And so obviously you can think of that as like 14 24ths of the total. So when you do that, you're going to have 14 divided by 24. So you're going to say, okay, it's 50 or 0.583 of the total. Repeated of the total. And so what we tend to do is we multiply by 100, stick a percent sign on it, and we end up with this answer of 58.3 repeated percent, right? So we know that the frequency, the number of people saying they're going to college is 58.3%, right? So the next step is to get that angle. Well, the total number of angles in a circle is 360 degrees in total. And so the angle for this one, right, would just be 58.3% of 360, which looks like this. We do 0. We convert to, I should stick a percent sign on that. Convert to the decimal equivalent, so 0.583 repeated times 360, and we end up with our number. So we have our 0.583 number times 360, and so it's 210 degrees. So what I would do here is I would, approximate the middle there. I'm just going to go on half. So we know that's 180 so far. And then we need an extra 30 degrees, right? So an extra 30 degrees or so. But you would just, you just measure with a protractor and measure out the angles. So that this needs to be the 210 degrees, and it represents 58.3% repeated percent, and label it as college. Oops. What is college, right? So this one is, I don't think you'd normally put this on the actual thing, but it's the 210 degrees. So let's just put it here for now. 180 with an extra 30, right? So we have the 180 plus the extra 30. That's just to help show what we did, but in your actual product of your pie graph, you wouldn't include that. Of course, you just maybe have it in your work that you've shown. Then the same kind of results for the other ones. This one would have been 4 out of 14. And notice that we eventually do multiply, right? So just to streamline this a bit, 4 out of 14 really times 360. That just combines all of that logic into the result. So we do 4 divided by 24, actually not 14. I'll correct that in a second. And then that number, of course, multiplies on the 360, gives you 60 degrees. Okay, so this should have said 24 in the bottom and gave us 60 degrees. And so the extra 60 brings us right to 90 there. So that's an extra 60 degrees. But of course, it represents what? The 4 divided by 24 was 0.166 repeated or whatever, so 16.7%. And that one is university. Or uni for short, as they say these days. And the final one, we have, let's go purple or something, this one's 6 out of 24, right? So 6 out of 24 times 360 equals, and you'll hopefully find that it's 90 degrees, right? So the 6 out of 24 is a quarter, 0.25, and then so 25%, right? Times 360 gives us the 90, of course, right? So it works out as it should. There's our 90 degrees, and it's our 25% going to a job of some sort. So that's how you do a circle graph. Pretty easy. Just maybe you haven't measured or thought about angles in a while, so brushing up on those skills. But yeah, so there's the resource version of it. But we did all that stuff. Very similar picture. I happened to choose my college half portion on the same part as them, or otherwise it could have been, rotated any angle and it would have represented the same thing, of course. So there's other ones to try, like I have listed as practice or whatever, but you can try this one and then check and see if your graph matches. But I think that's enough practice for us right now in the video, and your practice sheet's there for the one that you're doing officially to hand in. Right? So this question number 2, they gave you the percentages, so you don't need to even calculate the percentages. You're just calculating the angles, drawing it. This one, of course, you'll need to do a tally chart, get your percentages, convert them to the angles, draw your pie graph sections. All right. So there we go. Let me know if you need any help. Till the next lesson. Here we go.